Okay, so second derivative test, when the first derivative equals 0, that tells us, so if we know the first derivative equals 0, that tells us we have a horizontal tangent, right? So at a horizontal tangent, if we know that the second derivative is greater than 0, that tells us that the function is concave up. If the function is concave up there, and we have a horizontal tangent, we would know that we have a relative minimum at that point. So you do have to know the first derivative, but you only have to know the first derivative at that particular point, and then you only have to know the second derivative at that particular point. So for second derivative test, you don't have to make any sign lines. You still have to find the first derivative and find the second derivative, but you don't have to make a sign line. If we know that the second derivative is negative at that point, then we know that our function is concave down at that point. If the function is concave down and has a horizontal tangent, then we know we're looking at a maximum point there. Here's the reason I don't like second derivative test. If it so happens that your second derivative is 0, the test fails. You cannot make a conclusion. You have to go back and do the first derivative test all over again. So second derivative test, we'll see on this easy example, is not that hard. It's pretty simple, although first derivative test not that difficult either on a simple example. Second derivative test, if the second derivative is complicated, I do not like, because I don't like having to find that difficult second derivative. But there are some times they're going to force us into it. So on these problems here, we are going to use second derivative test. The problems you have from your book tonight, I want you to use the second derivative test, or at least try, because we already know first derivative. A lot of those first derivative will work on, but we want to use second. Okay, so when I say first derivative test, what I'm talking about is taking your first derivative, finding the critical points, and doing your sign line with the positives and negatives. That is your first derivative test for finding maximum minimums. So if we're going to use the second derivative test instead, we're going to take the derivative, which is very simple for this one. We're going to get 2x minus 6. We do still need to know where that equals 0. So we'll have 2x minus 6 equals 0. So that will be 2x equals 6. X equals 3 is the point that we're looking at. So we know x equals 3. We have a possible extrema at x equals 3. Now, if we were using first derivative test, here's where we would make our line, put 3 on it, test positive and negative. But for second derivative test, we're going to take the second derivative, and that's just going to give us 2. And we would plug 3 into that, but for this particular problem, plugging 3 in is really just going to be 2 still, right? So since that is positive, it tells us that f of x is concave up. So if we have a graph that is concave up and we have a derivative that is 0 at that point, we're looking at a relative minimum. I like to draw the picture because sometimes I get them mixed up, because concave up makes me think maximum, because up and maximum seem like they go together, but it's the opposite here. So we would say since f prime of 3 equals 0 and f double prime of 3 is greater than 0, f has a relative minimum at x equals 3. I guess this one did not just say x value, so we could say that minimum value is, and if you plug in 3 here, f of 3 would be 3 squared minus 6 times 3 plus 7, so 9 minus 18 plus 7, negative 9 plus 7 will give us negative 2. Or we could just say that there's a relative minimum at the point 3, negative 2. Okay, questions about this? All right, let's look at another example. All right, so we've got relative extrema for f of x equals 2x cubed minus 5 halves x squared minus 4x plus 2. This doesn't say use second derivative test, but I'm telling you that we're doing second derivative test notes, so we're going to use that. So for second derivative test, we always take our first derivative. And Paul, what are we going to get for our first derivative?
6x squared minus 5x minus 4.
Very good. And we still need to find where this equals 0, because for second derivative test, your first derivative has to equal 0. So, hopefully this is going to factor 3x and a 2x. And four and 1 right here, 4, negative 4, positive 1, does that work? That'll give you negative 8, positive 3, which is negative 5. Yeah. So you got 3x minus 4 equals 0, and 2x plus 1 equals 0, so 3x equals 4, x is 4/3, and here we've got 2x equals negative 1, so x is negative 1/2. All right, so these are our critical points. If we wanted to do first derivative test, we could put them on a number line. We could check signs using that chart, right? But they told us to do second derivative test, or I've told you to do second derivative test. So we're going to take the second derivative, which is going to be 12x minus 5. So we need to check each one of these points. We got to plug these in. So we're going to do f double prime of 4/3. So 12 times 4/3 minus 5. This is going to be 12 over 1. You could reduce that 12 and 3, so it would be 4 and 1, so you'd get 16 minus 5, which is 11. So that is greater than 1, or greater than 0. It's positive. You would also check f double prime of negative 1/2. And that will be 12 times negative 1/2 minus 5, which is negative 6 minus 5, which gives you negative 11. So for each one of these, you're going to make a conclusion. So we would say, since f prime of 4/3 equals 0 and f double prime of 4/3 is greater than 0. All right, let's think about this. Greater than 0 means that f is concave up. And so if we have a horizontal tangent there, we're talking about a minimum. Since both of these are true, f has a relative minimum value at x equals 4/3. And for the sake of time, let's find the x values of relative extrema. You would just plug that back in if you needed the y value if it asked for that minimum. And then for the second one, we're going to say since f prime of -1/2 equals 0 and f double prime of -1/2 is less than 0, f has a relative maximum value at x equals -1/2. And reasoning here, if I have a negative second derivative, that tells me my graph is concave down. And if it's concave down and has a horizontal tangent, we're looking at a maximum point there. This is not necessarily easier for a lot of functions than first derivative tests, but not necessarily more difficult either. Okay, and now that we know both, unless it specifically tells you to use one, you may use either one, except for on this homework, which I want you to do second derivative test to get some practice with it. All right. Okay, so this one asks us for relative extrema and points of inflection for this function. So, in particular, one reason that it may be helpful for this one for you to do second derivative test is because you've got to find the second derivative anyway, although we're going to see possibly some issues. So if we take our first derivative here, we'll get -15x to the 4th plus 15x squared. We do need to know where this equals 0 for critical points. So if I factor out a 15x squared, I would have -x plus 1. No, -x squared plus 1. And so I'd get 15x squared equals 0 and -x squared plus 1 equals 0. So this is just going to be x equals 0 right here. Here, you'll move that x squared over, so you'll get 1 equals x squared, so x is going to equal plus or minus 1. For our second derivative, we would get -60x to the 3rd plus 30x. Of course. Is that one with the cream cheese ice? Yeah. All right. For the extrema, we would be plugging in, just plugging in right here, right? So f double prime of 0, what do you get when you plug in 0? What does 0 tell you? Yeah, test second derivative, this is why I don't like the second derivative test, test fails, you got to go back up here and make a sign line. So -1, 0, 1. And if you plug back into that derivative, 15x squared is always positive, right? So if we're making a chart, it's always positive. If we plug into -x squared plus 1, if we plug in something like -2, we'll get a negative. Right here in the middle, we'll get positives for both of those, and then we'll get a negative again here. So at 0, you actually do not have a maximum or a minimum because your first derivative does not change signs. Yes? This is f prime of x here. So I had to go back, because this failed, I had to go back to the first derivative. So I was plugging into this equation right here, or this one, whichever version of that f prime you want to look at. So 15x squared is always positive. I didn't really worry about it. Plugging in -2 here, you would have -2 squared plus 1, which would give you -4 plus 1, which would give you -3. So you're plugging into the first derivative because second derivative test failed there. And while you're doing this, since you're already doing first derivative test, you might as well go ahead and find the other ones also. But if you wanted, you could still use second derivative test for -1, I believe, because you'd have -60 times -1 cubed plus 30 times -1, which is going to give you positive 60 minus 30, which will give you 30. So second derivative test does work for -1. It will also work for positive 1 as well, because f double prime of 1 is -60 times 1 cubed plus 30 times 1, which will give you -60 plus 30 equals -30. So on this one, you could either say that you have, so like what you could write here is you could say f has a relative minimum at x equals -1 because, and then you got a couple options here. It depends on which test you want to use. You could, where did my mouse go? There it is. Okay, you could say f prime of x switches from negative to positive. So that would be first derivative test. That's what we've been doing before now, right? Or you could say f prime of -1 equals 0 and f double prime of -1 is greater than 0. And I guess right here I could say positive than that. Something's not working right. My computer today, my mouse is now. I wonder if my batteries might be low. Again, the request says batteries on the mouse. I don't know. Anyway, you guys get the idea here. You can do the same thing for the positive one. So it's not letting me type anymore. So f has a relative maximum at x equals +1 because, and then again, you could either say f prime of x switches from positive to negative. I'm being lazy here, but I want us to get to the last couple problems. And then f, or we could say f prime of 1 equals 0, and f double prime of 1 is less than 0. So you could use either one for that. That one asks us for points of inflection as well. You would make a sign line, look at the sign changes for your second derivative for that, but I want us to get to these last couple questions that are more like AP Classroom questions that are like you'll see on your exam, so I am going to skip that for the moment. So this is the sort of stuff that they will do to you sometimes on the AP exam. They tell us f is a function such that we know f of -1 equals 1, and at each point on the graph the slope is given by this. Which of the following statements is true? Okay, so you cannot do a sign line when you have implicitly defined functions, right? Because there's an x and a y. So we can't just look at like the x coordinates because we also have to consider the y coordinates as well. So, I know that they've given me this information for this point -1, 1. And if you look at everything here, everything's talking about at x equals 1. All right, so this is the condition that we're going to use. So if we look at the derivative, at -1, 1, I would have -1 squared minus -1 times 1 plus 1 squared minus 1. So I'm just plugging into the derivative here, plugging in those x and y's. So that would give me -1 plus 1 plus 1 minus 1. What does that give us? 0, which is good because if you have implicitly defined functions, you're going to have to use second derivative test, and you can't use second derivative test unless the first derivative equals 0. So you are not done here, but this tells you that you can use the second derivative test. So now you need to look at the second derivative of that, which means you've got to take the derivative of this implicitly defined function. So the second derivative would be, we'd get -2x. What have I got to use for this xy right here? Product rule. So we got to do x times the derivative of y. What is that? dy dx plus y times the derivative of x, which is just 1, plus we'll have 2y, and we'll have a dy dx with that, and then the derivative of 1 is just 0. So this seems like it is complicated because like you got this dy dx, and you may have to plug that. You could plug this stuff in for the dy dx, which would make it incredibly complicated. But we only care about this at one singular point, at the -1, 1. So what we're going to do is we're just going to plug the point -1, 1 in for our x and y. I'm sorry, that shouldn't be, that should be x, y equals. And what does dy dx equal at that point? 0. So when I see that dy dx, I can just replace it with 0. So it's not going to be very complicated to plug in. So we'll have -2 times -1 minus 1, no, -1 times 0 plus 1 times 1 plus 2 times 1 times 0. So that'll give us +2 minus 1 plus 2, and we will get 3. No. Take that back. It's still going to be positive, but this is 2 times 1 times 0, so that's 0 right there. So we get a plus 0, so we get 1. So we have found second derivative is positive, which tells us that our function is concave up there, our expression is function. And we have a relative minimum at that point. Yes? I don't think so, because this will be 0. Yeah. And it may be different if you like distributed your negative, but you still should get a minus 1 right there. Okay, so we got relative minimum at that point, so A would be our answer. So implicit, you're going to have to use second derivative test because you can't make sign lines for implicit. All right, let's see what we got here. Let's look at this real quick, okay? Tables is another way they can do this to you because you can't take derivatives and plug things in. So let f be a twice differentiable function, and we're having to tell what's true. So f has neither a relative minimum nor a relative maximum at x equals 1. Then we're looking at x equals 1 and then x equals 4. So what are 1 and 4? They are critical points because our derivative equals 0. So if we look at the second derivative here, I have a negative, which tells me that this is going to be concave down. So what do I have at 1? A maximum. All right. At 4, this is a critical point. I have a positive for my second derivative, which tells me that this is concave up. And so I have a minimum. So maximum at 1 is true. Maximum at 4, is that true? No. We have a minimum at 4. And then neither maximum or minimum at 1, obviously 1 and 2 cannot be true at the same time. So we would just have 1 as true. I'm sorry. Yes, sorry. That's one of those things when you get your test back, you really regret your stupidity if you see it. All right. And we don't really have time for that. All right, so let me look through these and make sure they're the ones I want you to look at. I do want you to do second derivative tests for these. Let's see. Definitely 37 will be fine. 41 will be fine. 43 is okay. Okay. 44 and 53 should be the only ones that are kind of difficult because your second derivative will be a little bit difficult there. The other ones should have pretty basic second derivatives there. So I think these are fine.